Hello. So I'm going to talk about the formal verification of consensus protocols. So to understand why, let's first ask the question, where the Web3 community is heading to, right? Ideally, we would imagine that we will have a iterate this evolution of Web3 community. Right now, it's a high heterogeneous web of different kind of blockchains, and each of them have ledgers, consensus mechanism, and smart contract running on top, and they might interoperate, and you might do cross-chain exchange, and so on. The two major challenges remaining is the security and performance. And you always wonder, every day whether there's any bigger attack on certain blockchains. So naturally, the question would be, how do we make it even more secure and high performance? So the core problem is the consensus algorithm used in these blockchains. And you would wonder, it's kind of like an operating system kernel of a computer system, right? It's at the core. But these consensus algorithms are actually very tricky to implement. And so this is a challenge. How do we verify it? And indeed, because they are very tricky, so there's already many well-known bugs for even simplest kind of a consensus algorithm. So let's dive into it. The kind of consensus protocol we want to verify is the so-called Byzantine consensus protocol. And the property we care about, like safety, which basically says whether these a set of network nodes implement a consensus protocol, implements an atomic state machine. And of course, because these network nodes has to invoke a command, and there's a latency, so it cannot be fully atomic. So you usually use the notion of linearizability to say that the network of nodes implement an atomic state machine. Then you also have to guarantee liveness. You want to make sure every client command is actually eventually executed, and you have to make sure that you can deal with the nodes with different kind of fault model, which we care a lot about the Byzantine faults. So this is the kind of problem we deal with. And what the communication model for these Byzantine consensus protocols, often there's a asynchronous model where you don't have any guarantee, any message take an unbounded amount of time. Synchronous means every transmission takes a fixed delta upper bound. And partially synchronous is a kind of in between where you expect there will be a unstable time where message might take a while, but after global stabilization time, you will synchronize down to a bound delta. So it's called partially synchronous. And for this talk, I'm mostly going to talk about the consensus protocol under the partial synchrony. So the kind of a consensus protocol in these models is you are trying to follow this so-called round plus pacemaker paradigm. You divide the consensus into a set of rounds, and in each round, multiple nodes try to send a message across each other and try to reach an agreement. And so you need something called a pacemaker to make sure that all these non-faulty nodes are roughly in the same round. And this is not easy to do. And so you need something roughly works like a timer or pacemaker. And how do you implement such a pacemaker? You typically use, you have nodes when they don't see any reactions, you will broadcast timeout until no progress, when no progress in the current round. And then if you collect 2F plus 1 timeouts, then you enter round R plus 1. And you would think this is all you needed, but it's actually much more tricky. So is this going to guarantee your liveness? No. It turns out, it's a distributed protocol on its own. And so it would work, you have some assumption about the network gossiping model. And in fact, if you go to look at the detailed implementations, there's many little conditions down in these, if you vary the different conditions when you decide to send out a timeout, you will get very different liveness result. So this basically says that consensus protocol is much more than just reaching a consensus, but you also have to incorporate different kind of distributed protocols. So this is where our new methodology tried to accomplish. We developed this called LiDO model, where we don't try to describe the consensus protocol at the network model level. Instead, we will start from the state machine replication, which is an atomic model, and then we build a slightly lower model, which have a set of proposals, send a command to this machine, and have an abstract pacemaker ensure that the behavior of this protocol is working. And then right below it, so this would be what a proposer would do. A proposer will try to become a leader, calling something called a pull command, and then invoke a method and then try to commit it. And so this level is still pretty high level. And then down below, you would, because there's a bad host, and so you need a set of voters to make sure that the proposer is not doing bad thing. And then further down at the layer below, you would add back all these network level nodes. So you can see if you actually work at the network model level, there's many different functionalities. And some of them are used to implement the pacemaker. Some of them use to implement the consensus. And if you reason at this level, it's much easier. So then if you want to reason about liveness, you could imagine that you have a pacemaker that would logically help you allocate 2k plus 1 delta time, and then you divide these into different round and phase, and in each round you try to guarantee that something become a leader, broadcast request, receive the votes. And you need to make this thing generic so that it can be used every places. So this is just one part of try to prove the safety and liveness of the simplest kind of consensus protocols. It turns out if you want to have a better high performance consensus protocols, you need to even worry about these other issues like leader bottleneck. The standard consensus protocol, for example, have only leader may propose block, so this network throughput is very limited. The other processes are doing nothing, which is a significant resource underutilization. And if the leader is faulty, the network may not progress for long periods of time. So there have been, in the last few years, there has been a lot of DAG-based protocol which try to let every node issue a message at every period. And so this significantly increases the throughputs, and you can actually immediately invoke and commit a large number of messages in very small amount of time. And so this is actually a very active field. So this, in just 5 years, there has been a lot of asynchronous and partially synchronous DAG protocols. So what we have been doing recently is try to develop this LiDO, which is a pacemaker-aware model of partially synchronous consensus protocols. And we also extended the LiDO to support these leaderless mempools and DAG-based consensus protocols. And we then use them to build, I think, the world's first mechanized proof of safety and liveness for both these unpipelined and pipelined Jordan, and a set of DAG protocol like NAWA, Bullshark, and Selfish. And I think the nice thing about our proof is it's refinement-based. So you can actually link, you can push our proof is verifying actually executable OCaml code, but it's possible to link to low-level C implementation, and then you can use our LiDO model to link to the high-level model as well. So let me try to dive a little bit to show you how we actually implement, how the LiDO model actually works. So our work based on previous work called atomic distributed objects, which has been used to verify Paxos and Raft style reconfiguration in the past. So what's the idea? So the ADO model is basically try to create a high-level concurrent object-like model where you have these command called pull, invoke, push. So every proposal is try to become a leader by calling pull operations, and then invoke a method or method, and then you try to use push to commit a method. And the problem of this protocol is it's an atomic model. So if you want to read about liveness, you cannot reorder them. The temporal property cannot be actually formally stated on the atomic models. Where what we did in LiDO is try to reformulate ADO not as an atomic one, but as a linearizable object, concurrent but linearizable object. And another one is the ADO model does not have a pacemaker. So in LiDO, we actually add a pacemaker, abstract pacemaker state. So roughly speaking, you can imagine now we have a high-level model that is actually, you can reason about it as if it's a consensus mechanism, but it's not a distributed protocol. It's a concurrent-like protocol. And we added a logic pacemaker, which basically have several commands. You have a start next primitive, which is called by leader of round R. When you call it, the round will increase to R+1, and it resets the remaining time. And then you have a implicit global timer. It will call elapse when the time of this round is over. And or it will, if there's a timeout, it will be set the remaining time. When remaining time is 0, it will call timeout and resets the remaining time. So I can show you how it roughly works. So you start with so at the top right, we have the pacemaker state. This is the abstract pacemaker state. You have a round being 1, remaining time being 6. This is the set of committed consensus log, which is initially empty. We use a cache tree-based model to simulate what the LiDO and the ADO does. So first, in round 1, you have a proposal try to create become a leader. We add an eCache node, and then we try to invoke a method A. Unfortunately, right now there's a timeout. Maybe we haven't go outside the GST yet, and so we add a timeout cache to signify this current round didn't succeed. And then we try to go into round 2, where another proposal becomes the leader, and try to invoke a method B. And again, you hit a timeout, and this didn't quite succeed. And then you enter into the round 3. This time, this proposal tries to propose the method C. And this time it succeeds. And when you succeed, it actually remembers both the A and C added to the committed consensus log. So this just shows you how you can actually model a consensus protocol at a pretty high level, and you can reason about its both safety and liveness. So how do you prove liveness? High-level idea is actually quite simple. You only assume finite number of events every finite period, and then you basically divide the time dimension into these so-called partial synchronous GST and GST plus delta, GST plus 2 delta, and then you can actually have this following partial synchrony properties, which basically says that if a message was sent before the beginning of a period of delta, then it's definitely deleted at least once by the end of the period. So now using this so-called segmented trace, we can actually exhibit good properties. So how do we actually prove liveness? We can actually talk about the segment trace at the very high level, LiDO model level, and the reasoning about a set of safety conditions. And then we can prove the liveness at the very high level and showing new methods are committed infinitely open. And then we actually just prove these are all live network traces, refine the live traces of LiDO. So it's as simple as that. And when you actually verify concrete protocol, the actual concrete protocol will have individual network nodes to, you have a main process, receive request, and you have a local timer, which actually calls the reset timeout, and you use these to implement a network model level protocol. And so, for example, unpipeled Jordan is a well-known consensus protocol that we have used to prove. And we also proved the pipelined version. So this proof took about 4,000 line for the safety proof and 1,700 line for the liveness proof, which is actually a pretty moderate amount from the formal verification point of view. Then we actually moved to verify the DAG protocols. So as I mentioned before, there's a multiple kind of these so-called DAG protocols. Now our flavor is the consensus implemented using off-the-shelf BFT. Basically, DAG is only used to do the mempool operations, and the Burchak flavor is the consensus implemented on DAG itself. So we actually, roughly speaking, even though this DAG protocol is very sophisticated, you can, at the very high level, you can imagine at the LiDO level, all it's doing is just building a DAG and then use the rest of the service offered by LiDO to do pull, push, and invoke. And it's very easy to understand. So roughly speaking, the LiDO model only added 2 commands called DAG pull and DAG invoke. The DAG pull will simply, for a proposal to find out, what DAG has been constructed so far, and the DAG invoke will add a node to the existing DAG, and then it can coordinate with the rest of the LiDO model. So instead of just invoke one method as in the previous LiDO, you actually you can imagine the DAG model will tell you anytime when a LiDO try to invoke a method, now actually you invoke a sub-DAG of this DAG protocol. So you can do the invocation of these DAG protocol in batch, which is how it actually works. So roughly speaking, you can actually use this idea that even though you have many different ways to implement DAG protocols, so the physical DAG-based DAG protocol have sophisticated DAG and OGA-in algorithms, and those NAWA-based, you have a separate consensus protocol. We try to show that all these actually implement our high-level LiDO model, and they all follow this high-level protocol that look like this. So we have verified multiple DAG-based protocols, and there's NAWA, there's Burchak, there's Sailfish, and they roughly take also a few thousand lines, and it's fairly fast to verify these protocols. So we are now working on try to use the same methodology to verify even more sophisticated protocols like mysticity, which is used in the SUI blockchain. And we are try to verify asynchronous consensus protocols, as well as some of these other protocols that you see in Tendermint, Casper, or Gasper, and flexible consensus. So at the very high level, what we are trying to do is consensus protocol do not have to be understood and reasoned about at the very lowest level. In fact, if you try to do that, it's very difficult to understand and manage the level of complexities. All you need to do is to actually try to lift the abstraction at a very high level, and you deal with one feature at a time, and this refinement-based idea allows you to manage these. And so if you are interested, you can check out our papers. Okay, I will stop here.